In this video, we will be discussing recursive models, and we'll be talking about the geometric case. Now, some of you may have heard the term geometric growth before, and sometimes there's confusion about the difference between geometric growth and exponential growth, and the two are really related. And in the case of geometric growth, we think about sometimes we think about it in, well, what it is it's the type of function that it is its domain is discrete. So the big difference between geometric models and exponential models has to do with the nature of the variable being modeled, or variables in this case. And a lot of times the variable is time, and that'll be the case in the example I'm going to do in this video as well. And in the case of the geometric model, we think about time as being in discrete steps, or sometimes they're referred to as time steps. So in this, and that's the difference. So geometric models and exponential models are really the same, with except that one, the geometric model has a discrete type of a domain, while the exponential models have a continuous domain. And really, when I'm talking about domain, I'm talking about the set of possible input values for the model. And a lot of these models, and like I said earlier, involve time. So what I want to do is kind of go through this whole idea using an example. And the example, if you look at this picture, some might recognize the peak in the background. It's quite a beautiful peak. I'll give you a hint, it's in Oregon, the southern part, and this is Mount Thielsen. And the lake is Diamond Lake. And this lake is very well known for excellent fishing. And in fact, the real focus on the lake, I think, is fishing. It has a 10-mile an hour speed limit, and so it's not about water skiing, stuff like that. This lake's really about fishing and other types of recreation. Any case, so and originally, from what I've read, Diamond Lake probably didn't have any fish in it. And certainly rainbow trout would not be the native fish for this lake. I'm trying to remember the name of the Oregon trout. I think it's the golden trout is the native species, but I could be wrong about that. But in any case, this lake was stocked in the early 1900s with rainbow trout, and I think maybe another species. I'm not completely sure about that. And for many years, the lake was producing really big, large, nice trout. And I know from experience because I used to fish on this lake when I was a kid. Well, sometime in the late 90s maybe, or early 2000, this invasive species was introduced illegally, and it's the toy chub. And this fish really is an issue for the lake in terms of sport fishing. These fish have exploded, or their populations grew tremendously, and the rainbow trout species was in severe decline. So the Oregon Fish and Game had a real quandary, and in 2008, what they decided to do was to kill the lake, and they poisoned the lake. I'm not sure how to say the name of the compound. I think it's rotenone, or known. It would be known, bossy E, right? Rotenone, which is a naturally occurring compound from the pea family, and it suffocates the fish. And the idea is, the other thing that's good about it is it tends to dissipate. So after a period of time, it somehow, and I don't know the biological or the natural process, but it'll the lake water quality will come back. And so once all the fish are dead, the Fish and Game would come in, the idea was, or the plan was, and plant rainbow trout. And I believe I read that they also planted Chinook salmon, but I'm not 100% sure about that. But our focus is on the rainbow trout anyway. And so what we're going to do is talk about how we would model the population increase of introduced species like rainbow trout. And when we do, you hopefully have read in your reading assignments that when we approach mathematical modeling problems that involve the real world, we have to make simplifying assumptions. Otherwise, the mathematics and the equations become far too complicated, and it's even difficult to even know which variables in particular might be affecting the situation. And for this example, I'm going to make a few simplifying assumptions. For one, I'm going to say that the initial population of the fish is like a constant amount, or that I'm not going to. I guess I should put it this way: I'm not going to assume more fish are being introduced during the time period I'm modeling. So again, it is a simplifying assumption because they have stocked this fish annually with rainbow. But we're going to not think about that for now. We're just going to focus on the initial stocking and what happens with the population growth for that initial batch. We're going to assume that the resources in the lake for the fish's survival is unlimited. Obviously, again, this is an issue, but I'll come back and talk more in a different video about how we model that situation when there are not limited, or when there are limited resources. In any case, the other thing we need to know is by what proportion or by what fraction does the population reproduce itself? As it turns out, salmonoid species in freshwater lakes really don't spawn all that well. In other words, they will reproduce, and they do reproduce, but it's very slow. And so the assumption I'm going to make is 6% per year is how much that population increases annually. And again, going back to this idea of geometric growth, I'm going to model it using discrete time steps. In other words, when I model it, I'm going to think about the population on an annual basis. So if we and so again, I'm going to start. I'm going to make another assumption here. I need to have a starting place, and so I'm going to say they stock the lake with 50,000 fish, and that P sub 0 here again means the initial population. Well, what this means is after the first year, at a 6% growth rate, we would add 50,000 times 6%. I'm going to write that as 0.06. And so we could do this calculation, and that would give us the amount of fish in the first year. Now, in the second year, we're going to have the amount of fish from the first year. Oops, I wrote P1. Okay, that's fine, I guess. And then I'll have, which is this quantity right here. So I'll substitute that back in another step. But in any case, we'll have the P1, and then we'll have another 60% of that first year population. And so in this case, that would be 50,000 plus 50,000 and this is going to, you can probably see this is going to get complicated really quickly. And actually, I have to really concentrate here or I'll make a mistake. Okay, so what do we have? Well, we have, this is P1 right here. This is P1 again, and there's the times 0.06. Now, this is where some algebra skills can be handy because I'm going to factor out this 50,000 and write this as 1. That's what would be left here, plus 0.06. So this process is called factoring, and basically what I've done is I factored out the 50,000 is what we say, and you can tell this is correct because if I multiply the 50,000 back in, I'd have 50,000 times 1 plus 0.06, and I'm just going to write that as 50,000 times 1.06. Now, of course, I could simplify, I could multiply this out and write this as a number, but I want to leave that form to start seeing some patterns here. And remember, that's P1, and so I'm going to replace this quantity with this quantity, which are the same. And hopefully you're noticing the amount of arithmetic here can be pretty intense. I really didn't write that very well, but that's supposed to be a 1 and then a 0.6. So let me just cross that out. 1.06. 50,000 times 1.06, and then it's plus another 50,000 times 0.06 times 0.06. All right, so this is starting, again, this is complex. I understand that. Oh, not 0.06, doggone it, it's 1.06. 1.06. 1.06. Okay, that's better. And when I'm doing these kinds of problems, I often pause like I am right now and look things over and say, okay, do I have that written correctly? And I do believe I do. That's what. All right, so then this can be, and again, don't get lost in all this algebra, okay? I know I would understand if a number of you are saying right now, oh my gosh, what in the heck is he doing? I can feel that emotion. All right, times 1 plus 0.06. All right, so we got that, this whole quantity right here, I wrote here, this whole quantity up to 1.06 there was factored out. That's a 1. This is supposed to be a parenthesis. My computer's struggling a little bit right now, to be honest with you. That's sort of why I'm having trouble writing. If you listen carefully on the mic, you might hear the fan running. It's really getting hot. What? All right, I want to write that as 1.06. All right, concentrate, Todd. Okay, so now this is 50,000 times 1.06 squared. Now, one of the reasons to kind of struggle through all this algebra right now is I'm already beginning to see a pattern here. That's square. This is the second year population, and notice that's the initial population of 50,000 times this 1.06 squared component here. And so I think, or I know, we can take a shortcut here for the P3. Do we really need to do all this work? And the answer is no, because I'm already seeing the pattern. This next step will have a population of 50,000 times 1.06 cubed. And then I can do P4. So anywhere in this sequence now of future populations, I can write a formula for the nth year, we might say, sometime in the future. The population is going to be 50,000 times 1.06 to the nth. And we can write this in a very general formula that's in the textbook chapter. P sub n is equal to the initial population or size, P0, times 1 plus the growth rate to the nth power. And this is our geometric growth uh, model. We call this a model now. It can work for any population that's growing geometrically. We need to know the growth rate and the initial population to use the model. Now I want to show you a couple of characteristics. One of the other things that we do often is we graph. And notice this graph is made up of like a sequence of dots following along this curve. And I have the axes clearly labeled and scaled. Horizontal axis, which is the independent variable, time in years. The vertical is the number of rainbow trout. Now, one of the things we get interested in is something called the doubling time. And so one question we have often when we're dealing with geometric growth is, at what point in the future will the population double? Well, we started at 50, so doubled would be at 100 right here. So we would go across horizontally, and we would find a point in this curve and come and drop down and see, well, that's right about 12 years. It looks like the doubling time here is about 12 years. Now I go up to 200. Here's the thing to notice as I go up the Y scale. When I double when I double 100, I'm up here at 200. Okay, so remember, this was the first double right there, double 50,000. And now we're doubling this whole thing here up to 200,000. So come across here now. Let's just double check that I'm in the ballpark. Looks like the next doubling time, or the next time the population doubles, is 12 years later at 24 years. And then we can also look at 36 years. I added a few more years. This is 60 years into the future. So you can see that shape of that geometric curve is related to the idea that these doubling times are, each doubling time, this is like 50,000 to 100, and then to 200 to 400. So the doubling of the population has a powerful effect on the growth, and that's where that steepness of the curve comes from. And I just put a table in here too to kind of illustrate, here at 12, we've got about 100,000. At 24, we've got about 200,000. At 36, we've got about 400,000. So every 12 years, the population's doubling. One of the characteristics to look for in geometric growth to identify it is when we have a population that's increasing by a constant percentage each year. So in the case of the fish population, that percentage was 6%. Here's a really handy kind of rule to keep in mind, the rule of 70. To figure out this doubling time, all we need to do is to take the percent growth and divide 70 by the percent growth. So in the case of our trout population example, we would take 70 divided by 6. And again, I know this seems weird, but I'm thinking of it now as 6%. When I use it in a calculation, a percentage, we will move the decimal to the left. But in this calculation, I actually want the percent growth, the whole number in the denominator. So let's see, 6 times 11 is 66. That would leave 4, 6. So the doubling time here by this rule of 70 would be 11 2/3, which that's about, well, it's closer to 12 years than 11 years. So our visual on the graph of 12 years is also shown in the rule of 70 calculation. Okay, well, that's it for this video, and so I'll see you in the next video.